Okay, there's one exercise that was a little more difficult than the rest. Maybe I'll go through that. I don't think I assigned this one. Did I assign that? Yeah. Yes? Okay, let's do that one. Okay, that the limit of an is a says this: given epsilon bigger than 0, there is a capital N, so that an is between a minus epsilon and a plus epsilon for all little n bigger than or equal to capital N. Do you agree with that statement? That's what it means to have limit a. All right. So because of that, this is the limit we want to treat. There's an an in there. So let's replace an on one side by a plus epsilon, on the other side by a plus epsilon. Do you agree with that? Okay. And what does this side do as n goes to infinity? This converges to something. This one. E to the a minus epsilon. And this converges to e to the a plus epsilon. Okay. So maybe you remember, do you know the terms lim inf and lim sup? No? Okay. Well, if this limit exists, what does it have to be between?
E raised to the a minus epsilon.
Right.
To the a plus.
Has to be between this and that, right? So the limit, let's assume the limit exists. And this is true for every epsilon bigger than 0. See, no matter what epsilon I pick, this holds in the limit. And what can I do with epsilon now? I can let epsilon go to 0. Because the two ends squeeze down to e to the a, right? And any question on this? Okay, technically speaking, I should say, for those who do know this language, this holds, and then you let epsilon go to 0, and then you conclude the lim inf is equal to the lim sup, and that means the limit exists and is there a common value, which must be e to the a. So for a more rigorous treatment, if you've had these terms, I think you might have had them in calculus when you're talking about limits of sequences. But anyway, I think the idea is clear from here. And then this was supposed to be used in another exercise on the extreme order statistic for uniformly distributed random variables. And I forget which number that was. 29? Okay, number 29. So we take U1 through UN to be IID, uniformly distributed on the interval from 0 to 1. And then after you take your sample, you call the largest one that you see U sub parenthesis n. Okay, that's the max of that's the largest observation. And the exercise was to find the CDF, first to find the CDF for this. Okay, so let's find the CDF for that. That was the easy part of the exercise. Does everybody know by now what this stands for? Okay, cumulative distribution function. Okay. Well, the CDF for any random variable is this. If you put the random variable here, it's the probability that the random variable is less than or equal to x. It's a function of x. It's this function of x we're interested in. And this says what? UN less than or equal to x. UN is the largest of all the observations. So if the largest is less than or equal to x, well, the largest is less than or equal to x if and only if all of them are less than or equal to x. And these are independent, so this becomes, since these commas mean and or intersection, this becomes a product of the probabilities of U1 less than or equal to x, of U2 less than or equal to x, etc. And I could put the probability of U2 less than or equal to x here, and then a bunch of dots, and probably UN is less than or equal to x there. But what does this I mean in IID? Identically distributed. They have the same distribution function. So that you'd repeat the same thing over and over again, but how many times do you repeat it? N times. So we get that to the nth power. Okay. And what is this? Well, depends on x. If x is bigger than 1, it's 1. Why is that? What's the CDF for a uniformly distributed random variable on the interval from 0 to 1 look like? It's that, right? 0 until you get to 0. Then it's the function x, f of x equal x, and then it's 1. Why is it 1? Because if it's a uniformly distributed random variable on the interval from 0 to 1, the random variable has to have the value less than or equal to 1. So the probability that it's less than or equal to a number bigger than 1 is 1. If x is less than 0, then this probability is 0. All the numbers are between 0 and 1, so they can't be less than 0. The maximum can't be less than 0. Otherwise, if x is between then this thing is x, and we raise it to 10th power. Okay. Okay, let's find the expected value of UN. Well, I'll put 0 in there because I know the density will vanish off the interval from 0 to 1. Why? What's the density? Here's the CDF. The density is the derivative of this. What's the derivative of the constant function? 0. What's the derivative of this constant function? 0. So the PDF is 0 but for values of x less than 0 and for values of x bigger than 1. You should have here the integral from minus infinity to infinity, x times the density of UN. But the density vanishes off the unit interval, so I only have to go from 0 to 1. And what's the density between 0 and 1? It's the derivative of this. That would be, right, n times x to the n minus 1. And so inside here we get x to the n. The integral of x to the n is x to the n plus 1 over n plus 1, and we evaluate between 0 and 1. The value at 1 is 1 over n plus 1 times n, and the value at 0 is 0. So there's the expected value of the max. Now let's find the variance of the max. Well, that would be expected value of the maximum squared minus the square of the expected value. We just computed this. It's here. How do we compute this? Well, here we're computing expected value. We put x there. What would we put if we're doing squared? We put x squared there. Okay, and this becomes integral from 0 to 1 n times x to what power? From here we get x squared. From here we get x to the n minus 1. So that'd be an x to the n plus 1 altogether.
Well, you're getting the minus 1. I thought it was x to the n.
Okay, so here's the CDF.
Oh, yeah, right. Right, yeah.
And then the PDF is the derivative of that. Okay. So we get x to the n plus 1 when we multiply these two together. And this n is from the okay, and then minus n divided by n plus 1 squared. And this becomes n over n plus 2 minus n over n plus 1 squared. And let's combine this. We have to find common denominator. Common denominator would be n plus 2, n plus 1 squared. We have to multiply this by this denominator. And we have to multiply n squared by this denominator. And what does this become? When I multiply the first term out here, I get n squared plus 2n plus 1. But I multiply that by n, so I get n cubed plus 2n squared plus n. And here I get minus n cubed minus 2n squared. For a grand total of what?
N over that.
Just n is left. Okay. So there's the variance of un. Okay. So far, so good? Now, the exercise says something about the distribution of the standardized max. What's the standard normal distribution? Have we used that term? Has the book used that term? What do you think the standard normal would be? Mean 0, variance 1. So a standardized random variable means you somehow transform it so it has mean 0 and variance 1. How can you transform a random variable so it has mean 0? Subtract the mean. So we'd subtract n over n plus 1. And now, how can you make a random variable have variance 1?
Divide by the square root of the
Yeah, exactly. Divided by square root of the variance. Okay, so we'll take un, u parenthesis n, subtract that, and divide by the square root of this. And try to compute this less than or equal to x. Okay. For simplicity, let me call this sigma n squared. And maybe okay. Well, if this number is between 0 and 1, we know what this is. It's what? It's that number to the power n. So if and if it's bigger than 0, say, okay. Now let's put back in this for sigma n. Oops, this should not be sigma n squared here. Sorry, it should be square root of that, right? It's the square root of sigma n squared. So I better put square roots here. I do that because I can erase the 2 on the board, but I don't think you can erase the 2 in your notes. Okay.
Square root of n, square root. The square root.
Oh, right, yeah. There we go. Is that right now?
No, square root of everything except x.
Okay. I'll start again. Okay, so I should have square root of n over n plus 2, and then x over n plus 1 plus n over n plus 1. Okay. Can you see that? So the way to get from here to here is add a 1 here in the numerator and subtract a 1. If I add a 1, n plus 1 over n plus 1 is 1. And if I subtract a 1, that gives me minus 1 over n plus 1, which I put over here. Okay? Now, what was the exercise we did just a moment ago? It was if 1 plus, if an goes to a, then 1 plus an over n to the n goes to e to the a. We almost have that here. This would be the an. What does that converge to? Does that numerator converge to anything? What is this ratio, n over n plus 2? do as n goes to infinity? Goes to 1. So the numerator here goes to x minus 1. This numerator goes to x minus 1. And the denominator, is that n? Not quite. It's a quibble that it's not, but we can fix that. Let's replace this with n. But we want to be honest. We want to keep the same quantity we had before. So I'll put an n here. And then up in the numerator, I'll put n over n plus 1. So I'm going to rewrite this as, first I'm going to put the 1, because over there I put 1 first. Over n to the n. And then I'll put n over n plus 1 here times square root n over n plus 2 x minus 1. And that's equal to this. See this n plus 1? That's in the denominator here, right? So that means it's the same as being down here. And when I have an n up here and an n down there, what do? They cancel. So that gives that thing. Okay? Now, this is the an. And what does that do as n goes to infinity? N over n plus 1 goes to 1. N over n plus 2 goes to 1. So this whole numerator goes to x minus 1. So what does this expression go to then? What does this probability converge to? This converges to e to the x minus 1, so long as this is true. This should hold in the limit. Let's see what this says. Mu n is n over n plus 1, so this should say that x is less than or equal to 1 minus mu n over sigma n. And what does this do as n goes to infinity? 1 minus mu n is what's 1 minus mu n? That's converging to 1, right? So 1 minus mu n is converging to 0. In fact, 1 minus mu n would be n plus 1 over n plus 1 minus n over n plus 1 is 1 over n plus 1, right? This n plus 1 and this one down here will cancel. It's n plus 1 squared, leaving n over n plus 2 square root. And what does this do as n goes to infinity? Goes to 1. So this is good as long as x is less than or equal to 1. And the CDF for x bigger than that would be 1. So the limiting CDF for the standardized max What does this do when x is equal to 1? You get e to the 0 or 1. So this CDF looks like what? When x goes to minus infinity, this goes to 0. It dies off exponentially. Goes up to 1 at 1, and then it's flat. Okay. Turns out, if you ever go into insurance, This kind of random variable comes up a lot, the maximum. I think I mentioned earlier, why would an insurance company be interested in the maximum of a sequence of random variables? Well, the claims they receive on their policies are random variables, and the maximum would be the largest payout they have to make. And so they want to charge enough money so that they can cover the largest payout they have to make. So they want to know the distribution of the largest payoff. N is the number of claims they've received. So they probably are thinking about a large number of claims over a period of years. So they want to know how this behaves. So what they do is they have some distribution for the claims. May not be uniform, could be something else. And they subtract the mean, and they divide by the square root of the variance. And it turns out that this thing always has a limit, and there are three kinds of limits it can have. There are three different limiting CDFs you can get, depending on what distribution you start with. These are called the extreme value distributions. This is just one example of one of the extreme value distributions. You could start with another underlying distribution instead of uniform. You would get a different one. But in the limit, there are only three possible limits that you can get. So they're very interested in the distribution of the largest claim that they can get. And it turns out that in the limit, there are only a couple different kinds of limits you can get. And this is a very famous theorem in something called extreme value statistics. And this is all in the area of risk management. People are risk averse. Some people are risk averse. How many of you think you're risk averse? Okay. How many of you go on the roller coaster ride at the Gray Ghost at Knott's Berry Farm? Anybody go on that? So you're not risk averse. Okay. Or perhaps you invest your money in unwise companies, or perhaps you go to Las Vegas thinking you're going to win. Okay. But then on the other end, there are some people who are very risk averse, and they want to get rid of their risk. They sell it to somebody else, and there's a whole industry. And this whole industry of risk management or helping people who are risk averse uses a lot of probability theory. Okay, so that's it for those exercises. This is probably harder than you would have been able. Did anybody? Probably nobody was able to get this, but that's okay. So there'll be a new set of exercises posted today. They'll be due Friday. It'll be on chapters 6 and 7. And I think that'll be the end of the course. I don't remember what the syllabus said we're going to do. But I think we'll finish 6 and 7. Okay, so last time, we discussed chi-squared distributions. If Z is normal with mean 0 and variance 1, then I'll define it to be U equals Z squared is called a chi-squared with 1 degree of freedom. If Z1, Z2, Zn are independent normal 0, 1 random variables, then U sub n, I'll call it, equals Z1 squared plus Z2 squared plus Zn squared is chi-squared with n degrees of freedom. These come up in a lot of statistical analyses. Okay. Some other common distributions arising from the normal are what? If m and n are non-negative integers, and u is chi squared with m degrees of freedom, v is chi squared with n degrees of freedom, and u and v are independent, that's called the FMN distribution. Ratios are useful statistics to analyze data. Now, last time we did mention that the chi squared is actually a gamma. I believe is gamma of n over 2 and 1/2. That means this is the alpha, that's the lambda. Right. I haven't done a lot of computations where we compute PDFs or CDFs for ratios, so let's do that now with this one. Okay. So that would be the CDF differentiated so we want to differentiate this thing. Okay, so that means we should try to figure out what this is. Okay. Rather than write the derivative every time, I'm just going to compute this first, and then I'll differentiate afterwards. Let's multiply through by v over n. Does that change this sign at all? What were u and v? Chi-squares with m and n degrees of freedom respectively. What were chi-squares? Sums of squares of normals. So chi-squared random variables are always non-negative or positive. So when I multiply through by v over n, I don't change the direction here at all. And now I'm going to multiply through by little m. We're going to write this m over n v x like that. And using the independence of u and v, I could get to this. Now this maybe I should take a couple steps here. This is saying that the pair uv is in a certain set. It has to lie below, the pair has to lie below the line in uv space that has slope m over n x. That's this line, right? U less than or equal to that means, well, maybe I have the wrong one. U less than or equal to that means I guess we're we're above the line. The first variable has to be smaller than this multiple of the second. Okay. So the probability that U is less than or equal to m over n x v would be the probability that the pair u v is in that set A, that maybe I'll index it by m over nx. So this is the set A, m over nx. Is that too quick? At this set? Well, if the pair uv is up here, is it true that u is less than or equal to m over nvx? Here's the fixed value of v. If I go along this line here, horizontal line with constant y coordinate v, when I start out here, is u bigger than m over n x v or smaller? When u is 0, it's smaller, and it's smaller all the way up until I get to that line there. Okay, so this is the right region. And to compute a probability like this, you integrate the joint density over that region. Okay. But they're independent. So the joint density is a product of the individual densities. And now what we should do is set up limits of integration to describe where we're integrating. So our v can go from 0 to infinity, and for a fixed value v, u goes from here to m over n x v. Okay. So this is the integral v going from 0 to infinity, u going from 0 to m over n x v, f sub capital U of little u, f sub capital V of little v. Du is the inner integral, dv is the outer one. Okay? Now, let me kick this guy out. And what is this integral? It's the integral of the density for capital U from 0 to something. What's that called? 3 letters. Last letter is F. CDF. That's the CDF for U, evaluated at the upper limit. So I'm going to write that first. This is the CDF for U, so that's the probability that U is less than or equal to that value. Okay, so that's what I wrote here. All right. So always remember this. If you want to compute the probability of something about a pair of random variables, you need their joint density or joint distribution or joint probability mass function. And you express whatever this restriction is as a set. And you integrate the CDF over that set, or you sum the probability mass function over that set. Okay. So here that set was this. Okay. So this should be automatic every time. All right, so we got to this point. And we wanted to differentiate. So let's differentiate that expression. Okay. Well, here's the only place x appears, so we differentiate this. This is the CDF for u, so when we differentiate, we should get the PDF, right? But we have to use the chain rule. We're differentiating with respect to x, so we'll get this thing outside, right? So this will become integral from 0 to infinity, this PDF at m over n v x, because that's the derivative of this function of that variable. But then we have to multiply by the derivative of this with respect to x, which would be m over n v, and then we have the PDF for v. Okay, so that's the chain rule. Right? This is f, capital F sub u at m over n v x. So if we want to differentiate that with respect to x, we get capital F u prime at m over n v x times the derivative of what appeared inside with respect to x, that's m over n v. Okay? And this is the PDF now. This is little f. Okay. And then we have to integrate this from 0 to infinity. But you won't have to do any integration. Let's substitute what the PDFs are now. I wrote them on the board. There are going to be constants out in front. First one, I guess, will be m over n. From here. And then we take evaluate the PDF for u at m over n vx. Now u has these constants out in front, so let's put those out in front. And then v will have 1/2 to the n over gamma of a half. And then we take the value of this we raise that to the m over 2 minus 1. And then we raise v to the n over 2 minus 1. I promise you, it's not as bad as it looks. Okay, now what in here doesn't have a v? Well, this doesn't have a v. Let's pull that out, and the x doesn't have a v. Let's pull that out. Okay. Now out in front we have an m over n. Well, let's see. Let's take care of the halves first. We have a half to the, whoops, I forgot n over 2 here. We have a half to the m plus n over 2. We have a gamma of 1/2 squared. Here's an m over n, but we also have an m over n to the m over 2 minus 1. Yeah?
Maybe I'm missing it. Did you leave out the middle, so the v that you created from the chain rule above? Did you leave that out, or did I just miss that step?
Oh, you're right. Let's see. No? It's here. You're right. I didn't put it. I left out the v. Thanks. I left out the v. Yeah. I forgot to put this v down here. Okay, so m over n to the m over 2 minus 1. And here's an m over n to the first power. So we'll get altogether m over n to the m over 2. And so I think that's all the constants. Oh, forgot this one, x to the m over 2 minus 1. Then times integral, 0 to infinity, v to some power. What power? Here's the first power. Here's to the m over 2 minus 1. Here's to the n over 2 minus 1. I add all that up. 1 plus m over 2 minus 1 plus n over 2 minus 1. That is v to the m plus n over 2 minus 1. And then e to the minus v. Okay, so it's late. Let's take a break and come back in 10 minutes and finish it. Okay, so let's continue, but amend your notes. I put gamma of a half here. It should be gamma of m over 2. Remember, the gamma density is lambda to the alpha over gamma of alpha x to the alpha minus 1 e to the minus lambda x. So that should be gamma of m over 2 here, gamma of n over 2 there. So that shows up here. Should have gamma of m over 2, gamma of n over 2. And when I was evaluating the density for u at this, I did put that in m over nv x to the m over 2 minus 1 for the power, but I forgot to do that in the exponential part. So this should not be, this should be m over nvx here. I forgot to put I put v in for the exponential part. So I should be evaluating this at m over n xv. So that should go in here. It should also go in the exponent. I forgot to put it in the exponent. Okay, this is the density for u. Not to evaluate it here. I did it correctly there, but I forgot to put it in the exponent. Okay, so that'll show up when I do the exponents. I have an e to the minus v over 2, and then this. So if I add the exponents, I'll add minus v over 2 m over n x, and minus v over 2. I can factor out the minus v over 2. I get 1 plus m over n x times v over 2. Or maybe I'll write it this way, minus 1 plus m over n x over 2 times v. Okay? That's what happens when I combine these two exponentials. So once again, I forgot to put m over nvx in the exponent part of the density for u. I put it in the power part, but you also have to put it in the exponent part. And correct the densities for u and v to have a gamma of m over 2, not gamma of a half. It's m over 2 here. And for v, n over 2, gamma of n over 2. Okay? And that brings us to this here. And the last part I had to carry over from there is e to this power. dv. Okay, so how do we do this integral? We use the fact that this is a density, right? And in that, what is the alpha? Alpha is m plus n over 2, and lambda is 1/2 1 plus m over nx. If you compare, alpha is m plus n over 2. Lambda is half times quantity 1 plus m over nx. And so this becomes, let me put this down here. And here I'd get lambda to the alpha in the denominator. That'd be 1/2 1 plus m over n x raised to the power alpha, right? Which is m plus n over 2. This is the lambda to the alpha. Another way of saying this here is that integral from 0 to infinity x to the alpha minus 1 e to the minus lambda x dx is gamma of alpha over lambda to the alpha. So I've just put the lambda to the alpha here with lambda equal half times the quantity 1 plus m over nx, alpha equal m plus n over 2. And up here should go gamma of alpha. And, well, you can combine the x terms, but that's the density. Okay. So there are a couple of steps, key steps. One is if you're computing the probability distribution function for a ratio, you write that. If the denominator is always a non-negative random variable, you can multiply through by that and not change the direction of the inequality. And then you have to express this as the probability that the pair UV lies in some region. In this case, it would be above a line. And then you integrate the joint density for the pair over the region above the line. And if they're independent, the joint density factors. And the rest was just collecting terms, busy work, and then using the fact that you know that the gamma density is a density. And then you don't have to do any integration. Okay? It's kind of ugly, I have to admit. It doesn't look very nice. Okay, so another distribution that comes up is called the T, sometimes referred to as the student T distribution. This is called the student T distribution. Sometimes student doesn't refer to people like yourselves. It refers to pen name of a statistician who worked for Guinness. And he had to work with small samples. And to analyze data from small samples, he came up with this statistic here. We'll study this later. I'll give it to you as a challenge to compute the density for this. That would follow the same steps we've just done. How do you compute the density? You can write down the distribution function. What would that look like? You'd have a what? Instead of this ratio, you'd have a z here and a root u over n here. You could multiply through by the root u over n, so you'd have z less than or equal x root u over n. This is the pair, then that means the pair zu must lie in a certain region in space. Write down the integral over that region of the joint density. What's the joint density going to be for z and u? It's going to be a product of the individual densities. And then hope for some miracle. And there will be one. But I won't do it. The density is written down in the book, but see if you can derive it yourselves. Okay, so let's consider the following. Suppose x1 through xn are independent random variables. Well, for now, I don't need independent. The sample mean is just this, their average. And the sample variance I always forget. Yeah, right. Want to make sure it's 1 over n minus 1 here. N minus 1 goes here. The reason for that is if the x's are independent, or let's even say IID, with variance, common variance equal to sigma squared, then the expected value of s squared is sigma squared. This is supposed to be an estimate for sigma squared. If I have a 1 over n here, I wouldn't get sigma squared there. I'd get n minus 1 over n times sigma squared. If s squared is supposed to estimate some parameter, namely sigma squared, if the expected value of the estimator is equal to the true value, then we call that an unbiased statistic. So we normalize by 1 over n minus 1 here to get an unbiased statistic. Up here, what would the expected value of x bar equal? If we're in this situation again, if these are identically distributed, then the expected value of x bar is mu. Why is that? Well, what's the expected value of a sum of random variables? It's the sum of the expected values. So what would we get here in the sum? We'd get n times mu, but then divide by n, you get mu. Okay? So this is supposed to be an estimator for mu, and its expected value, when you take the expectation of the randomness, you get mu. So that's called an unbiased estimator. Its expected value is equal to the parameter it's supposed to be estimating. Okay. So let's examine the case where we have normal random variables. Suppose these are normal mean zero variance 1 random variables. which is often the case. Because of the central limit theorem, many samples and applications can be assumed to be normal random variables. Also, we have the fact that Poisson distribution, when properly centered and scaled, is close to a normal random variable, and binomial random variables. When we subtract the mean, divide by the square root of the variance, that's going to be close to normal. So a lot of the samples you get are assumed to be normal random variables. In that case, x bar is independent of the random vector x1 minus x bar, x2 minus x bar, xn minus x bar. It's kind of strange. X bar appears in both places, yet they're independent. So one way to prove independence is look at the joint density and show it factors. Another way is to look at the moment generating function and show that it factors into a product. If it does, remember that you use the uniqueness property of moment generating functions. A moment generating function can only come from one distribution. So if it comes from a distribution where the x bar part factors away from this part, then you know they're independent. So let's look at the moment generating function for this. For the vector value case, we have n plus 1 random variables here, so we need n plus 1 real variables, and here's what we do. We look at e to the t naught x bar plus t1 x1 minus x bar plus t2 x2 minus x bar plus etc. Tn xn minus x bar. And what we're going to do is we'll show that this factors into and that'll be enough to show independence. Okay? Okay, let's recall this fact. And let's start with the left-hand side. Okay, and what's x bar? Okay. So what do we get here? What's the coefficient of, there are a bunch of x1s in here, right? What's the coefficient of x1 in this expression in the exponent? What do we get for the coefficient of x1 from here? Well, x1 is the first term in the sum. It's multiplied by 1 over n, and then we multiply also by t naught over n, right? So maybe I'll just work with the exponent for a moment or two. Here I got t naught over n. Here I won't get a, what do I get here for the coefficient of x1? Is that right? And what do I get all along here? The next term would be t2 x2 minus x bar. So I'll get a minus t2 over n times x1 from here, then minus t3 over n, etc. And then here I get a minus tn over n, all times x1. And what do I get for the coefficient of x2? From here I get a t naught over n. From here I'll get a minus t1 over n. From here I'll get a t2 times 1 minus 1 over n. Then I get a minus t3 over n, etc., all the way up to minus t sub n over n times x2. And I keep going like that until I get down to the nth one. Okay. On the diagonal, I get t1 times 1 minus 1 over n, then t2 times 1 minus 1 over n, and all the way down to here, right? Let's recombine. There are terms with just like t1, t2, etc., right? So I get t sum I equal 1 to n ti times xi. Well, let's see. What do I get times everyone has a t naught over n, right? Every one of them has a t0 over n. Every one of them has for x1 I get a t1, for x2 I get a t2, for x3 I get a t3, for xn I get a tn. So I get a plus ti. And then I get a minus t sub I over n. Minus what? Sum of sum j equal 1 to n tj over n. I'm going to write that this way: 1 over n sum j equal 1 to n tj. So let's do this one first. If I have t naught over n times xi and add up I going from 1 to n, what do I get? I can fill out the T naught, right? And then I get a 1 over n times the sum of the xi's, that would be x bar. Plus the sum, I equal 1 to n ti xi. And then minus what? This thing I can call t bar. So we could rewrite it this way. This is not x bar, is it? But it's n times x bar. So I combine that with this. But actually, that's not as useful as I would like. I think I'll just stick with this. Let's just stop here. Okay, we'll use this one. Okay. So you don't need these. What I wrote is right, but we'll stop here. Okay. Now let's decide what kind of random variable is this. We have a sum of independent normal random variables. What kind of random variable is t naught over n plus ti minus t bar xi? That's a normal random variable. What's its mean? Zero. And its variance is t naught over n plus ti minus t bar squared. Okay. If I have a normal random variable, x is normal. If x is normal means 0 and variance 1, what kind of random variable is a times x? What's the expected value of this? 0 still. What's the expected value? What's the variance? The variance would just be the expected value of this squared. That would be a squared. Okay, so we just get this squared. So what kind of random variable would this whole sum be here? They're independent normals. The sum of independent normals is normal. This is a normal random variable. What's the expected value of this? Each sum end has expected value 0, so the whole sum would have expected value 0. And what about the variance of this? The variance of the sum is the sum of the variances for independent random variables. So the variance would be the sum of these things. Okay. Now let's examine what this variance is. If you have a plus b squared, it's a squared plus 2ab plus b squared. So I just did that. Okay. Now what's the first term here? All of these are the same. So I just multiply this by n. That would be t naught squared over n. Okay. What about this? When I add up this, what do I get? When I add up the ti's, I get n times t bar. When I add up these, what do I get? Well, they're all the same. I get n times this term. But I'm subtracting this from this, so what does this become? 0. This part is 0. Okay, so this random variable up there is normal with this variance and mean 0. Okay, so and that's what goes in this exponent. This random variable is normal with mean 0 and variance that. So this is equal to e to the mu is 0. Sigma squared is that thing over there. And so it's as though I have 1 here. 1 times this random variable. Okay. This is now my x. I'm taking t equal 1. So I'd get just the half the variance. T naught squared over n, or 2n, and then times e to the 1/2 sum I equal 1 to n ti minus t bar squared. Okay? So I find that the expected value of this thing, the moment generating function for this complicated vector form is this. What is the expected value of e to the t naught x bar? Can I get that from this? Is t naught x bar equal to what I see there for some choice of t1 through tn? Yeah, what choice? Take all the ti's to be 0 except t0. Then this will be 0, that'll be 0, that'll be 0. And what do you get here then? 0. So this would be okay. And what is this part? That's if I take t naught to be 0, that's what I get here. And what if I take t naught to be 0? I just get this. So what's the moral of the story? The moment generating function for this is the product of this moment generating function and that one. So what does that mean? It means this random variable x bar and the vector x1 minus x bar through xn minus x bar are independent. Okay, and the miracle was right here. The moment generating function for normal looks like this. It has this particular form. So when we're computing the variance, what happened? the T naught part separated from the Ti minus T bar part. And we're taking exponential of this, so that means it factors. That's why the factoring took place, because this term canceled. Okay, so X bar is independent of this when you have independent normal samples. All right, so this implies a very important result. X bar and S squared are independent. S squared, remember, was 1 over n minus 1, sum I equal 1 to n, xi minus x bar squared. This is a function of, use g of x1 minus x bar, x2 minus x bar, xn minus x bar, right? It depends on what? These differences. S squared is a function of these differences. X bar is independent of this vector. This is a function of the vector that's independent of x bar. So a function of, if you have two random variables, y and x are independent, that implies y and g of x are independent. Okay, so we're just taking a function of these things, and they're independent of x bar. So when you're dealing with sample means and sample variances, they are independent random variables if your sample is normal. It's not true if it's not normal. Okay, so we can stop there today. Have a good weekend.